we'll continue to the next session, next topic. So we'll go to Fourier series. Fourier series. So here any finite continuous single valued function. Any finite continuous and single valued function can be written as sine and cosine series. సో మనం తీసుకున్నటువంటి ఫంక్షన్ ఏదైనా కానీ ఫైనైట్ వాల్యూస్ ఉండాలి, కంటిన్యూస్ గా వాల్యూస్ ఉండాలి, అక్కడ బ్రేక్స్ ఉండకూడదు, సింగిల్ వాల్యూడ్ అంటే ఎక్కడైనా ఒక చోట ఎక్స్ తీసుకుంటే వాట్ ఈస్ ద వాల్యూ ఆఫ్ ఎఫ్ ఆఫ్ ఎక్స్ అంటే ఒకటే ఆన్సర్ రావాలి. దేర్ షుడ్ నాట్ బి ఎనీ క్రాసింగ్స్ ఆర్ ఓవర్లాప్స్. అలాంటి ఫంక్షన్ ఏది తీసుకున్నా సరే దట్ కెన్ బి రిటన్ యాజ్ సైన్ అండ్ కొసైన్ సిరీస్. సో దట్ ఈస్ ఫోరియర్ సిరీస్. సో మనకి తెలిసినటువంటి బెస్ట్ ఎగ్జాంపుల్ ఏంటి అంటే స్క్వేర్ వేవ్. స్క్వేర్ వేవ్ is a combination of స్క్వేర్ వేవ్ అనేది ఎట్లా ఉంటుందంటే ఇట్ ఈస్ ఫైనైట్, ఎక్కడ కూడా ఇన్ఫైనైట్ అనే నంబర్ రావట్లేదు, కంటిన్యూస్ గా ఉంది, ఎక్కడ కూడా బ్రేక్స్ లేవు, అండ్ సింగిల్ వాల్యూడ్. ఫంక్షన్ ఎక్స్ యాక్సిస్ మీద ఎక్కడ మీరు లైన్ గీసినా సరే ఫ్రమ్ ఎక్స్ యాక్సిస్ ఆన్ టు ద ఫంక్షన్ విల్ గెట్ ఓన్లీ వన్ వాల్యూ. So it is finite, continuous and single valued function, square wave అనేది. So it can be written as a series of sine and cosine functions. A series ఏంటి అంటే all odd number additions for sin n pi x by l by n. So ఇందులో ఆ న్యూమరికల్ వాల్యూస్ అన్ని నేను ఇగ్నోర్ చేస్తాను. 4 by pi, pi x, pi f by l ఇవన్నీ ఇగ్నోర్ చేసేస్తే it is sin nx by n, all odd numbers, n value takes only odd numbers, sin nx by n. So if I take that series, let's say square wave, so I'm taking 3 cycles. If I take from 0 to 2 pi, I'll get 1 cycle. If I take 6 pi, I'll get 3 cycles of square wave. My function is f is equal to 0, and I am taking n values from 1 to 9 with a step size of 2. Means 1, 3, 5, 7, 9. 5 combinations of n values I'm considering, and I'm calculating sin nx by n and adding it to f. And finally, I'm plotting f versus x. So I'll get 3 cycles of square waves. This line with percentage symbol is comment. So if you raise this count, you'll get more clear square wave. Next, we'll see differential equation solutions. So for that, we need a symbolic package. PKG. Okay, PKG load symbolic. Then Sims y of x. So this is my function. And I'm defining my differential equation, which is the equation of simple harmonic oscillator, a second order differential equation. So the diff y2 stands for d square y by dx square. Diff y2 stands for d square y by dx square is equal to minus 5y. Means the frequency is square root 5. The harmonic oscillator wave equation, differential equation. So I loaded a symbolic package. So till now we have dealt with numbers. Now we can calculate symbolic solutions also. So I loaded the package. I defined my variable y of x. Y is a function of x. Then I have defined my equation. So this is the equation. D square y by dx square is equal to minus 5y. Okay, so then we solve equation 1. That's the solution. C1 sine square root 5x plus C2 cos square root 5x. General solution. You can call that as another function. I call it as solution 1. F plot solution 1 gives me the functional plot. C1, C2 are not defined. So if we precisely define the initial conditions, we can get that C1, C2 values also. So what all did we do? PKG load symbolic, Sims y of x, equation 1 equal to if y comma 2 double equal to minus 5 star y. Five minutes. Last one. Yeah. Yeah, so this is the equation. Then solution. Equation 1, y of 0 equal to 0. If y of 0 equal to 1. So these are my initial conditions to solve the differential equation. Then I go for f plot solution. I save it as is the name sho.m. I got the graph sho.m. So that is the simple harmonic oscillator wave equation. And if we have damped harmonic oscillator, this is the damping factor 0.1. So if we solve that, get dampened. Let's say this is 0.3. You get damping like that. So you can write any kind of differential equation, solve symbolically. So the semicolon will get the output in command window. Whatever your differential equation solution, everything. Right. So with that, I'm closing this session. Right. So welcome to the second session on simulation tools for mathematical physics. So here we're going to deal with simulation tools required for solving mathematical physics problems using a computer and program. So I'm going to share my screen. So we'll be using MATLAB or Octave, which is a free version of MATLAB, to deal with this majorly. So this is related to the first year single major physics, especially that mathematical physics paper lab session. So you have 5 units in your syllabus. So in your physics major, you have mathematical physics. That's course 1. The units are this: vector analysis, linear algebra, complex numbers, probability, and Fourier analysis. So we try to work out a few problems from the lab session of this, like graph plotting for sin x cos. Okay, so you can use this even on your phone. You can try the online Octave online. Search for Octave online. Your phones. Search for Octave. Open the third link. My compiler. My compiler. Online Octave. MATLAB compiler. The MATLAB app already Octave. It's okay. Otherwise, you can use this online compiler. Octave Online and choose my compiler.in. My compiler. Okay. Here in MATLAB or Octave, MATLAB stands for matrix laboratory. So whatever mathematical operation that you do using MATLAB is considered as a matrix. Let's say x is equal to 1. Just type in x equal to 1 and run. Click on the green button for online compilers. So x is equal to 1. Output is x is equal to 1. And let's say size of x. So type size of x. You get 1 by 1. So even a single number is considered as a 1 by 1 matrix in MATLAB. Okay. So all mathematical operations are considered as matrix operations in MATLAB. So now we have to see what can we do using this. So let's say that size of x, you get 1 by 1. Let's say you have a set of numbers and you want to plot sin x. Let's say x is equal to 0 with a 0 to 2 pi with a step size of 0.1 up to 2 pi. These are x values, 0 to 2 pi with a step size of 0.1. Represented as 0 is to 0.1 is to 2 star pi pi. So here pi is also a built-in command which gives you the value of pi. So you get all the values of x starting from 0 to 2 pi means 2 into 3.14, 6.2. Up to 6.2 you get all possible values for x. Okay. So now plot x comma sine of x. You get a sine curve. Okay, so if you draw that, plot x comma sine x, get a sine curve. So you can add further terms also and arrange them all together at one place. So when you are using a offline compiler, go to editor. Go to editor and enter all the list of commands that you have entered till now. 0, 0.1, 2 star pi. Plot x comma sin x. If you click on run, you have to save the file. Let's say plotting.m. .m stands for is a MATLAB file. అది MATLAB file అని చెప్తుంది. File extension .m పెట్టండి. ఓకే, ఇప్పటివరకు ఎంటర్ చేసిన కమాండ్స్ నేను మళ్ళీ యాజ్ ఇట్ ఈజ్ ఎంటర్ చేశాను. x is equal to 0 to 2 pi with a step size of 0.1. I'm plotting x comma sin x. So I get the graph. So now you can add title, X label, Y label, all these labels can be added. TITLE, title, quotes, sin x. Gives you title to the graph. Okay. So you got a title. Then X label, X label. All built-in commands will directly come here. X label, X value, Y label, sin x. If we set all of them, you get a title for the graph, X label, X, Y label is sin of x. It's like that you can plot any graph by considering suitable data. And if you have 6 plots, you can plot all of them on a single canvas using subplot. Subplot అనే కమాండ్ యూస్ చేస్తే మొత్తం ఈ 5-6 గ్రాఫ్లని ఒకే చోట గీయొచ్చు. So I'm taking a 2x3 canvas and in the first place I'm drawing the sin x. 2x3 canvas అంటే ఏంటంటే 2 rows 3 columns ఉంటాయి. అందులో ఫస్ట్ ప్లేస్ నేను sin x కి ఇస్తున్నాను. Subplot 231. So that is my first plot. Then copy paste it and edit for the next one. Subplot 232 and I draw cos x. Label is also cos x. Now I got two graphs, one starting from 0, another starting from 1. Sin x and cosine x. Then other functions, log x and e power x. Subplot 233 log x. This is log x graph. Before e power x. E power x graph. That can be written as e power x. This is e power x graph. Next one is x square and square root x. X square. Go for 235. X dot square. So you have to use x dot square. That is a parabola. X square plot. And for square root x, it will be opposite to that. square root x. So for everything you have built-in functions. So this is the command for square root x. It's 6. They are the graphs for all the 6 functions with labels. So in the next one, I'm going to develop a plot vector fields. So I'm considering x values starting from -2 up to 2 with 8 intermediate points, means with a step size of 0.5. And along y direction also, I'm considering numbers from -2 to 2 with 8 intermediate points. And I generated a mesh grid using that x and y coordinates. So I generated a mesh grid. So now I'm going to define different vector fields. So one is radially moving outwards. So the vector field is also increasing along x direction in the form of x. And along y direction, it is also increasing in the form of y. So that it is radially moving outwards. This is the vector radially moving outwards. Let's say I'm taking this. Okay. So now I'm defining my vector field. U1 is equal to x and U2 is equal, V1 is equal to y. If you plot it, so this is the plot you're going to get radially moving outwards. So this is the vector field. So both x and y are increasing. So if you have to consider radially moving inward vector field, it will be minus y, minus x and minus y. Then the direction changes. ELUR gives you Next one is right circular. Right circular field, which looks like v1 is equal to minus y, v1 is equal to x. Right circular means the field generated using the curl of your right hand fingers. మన right hand fingers turn చేస్తే ఏ direction లో వస్తాయో that is right circular field. Okay, so it is given by minus y plus x. Title is right circular. Left circular is opposite to this. The signs will change. Plus y minus x. This is a left circular field. Can be generated with your left hand. Curve. Y minus x. One is saddle field, spiral field. X minus y, x minus y, and x plus y. Left circle, right circle, then saddle field is x and minus y. Saddle. Around a point from all the four directions, the field will be flowing. Field lines will be moving around a point. That's called saddle point. Next one is spiral field. X minus y and x plus y. Looks like that. Spiral field. You interchange that, the direction of the spiral will change. X plus y and x minus y also will give you a spiral. Saddle point. Okay. So x minus y and x plus y is a spiral. So these are different kinds of vector fields that we usually come across. Next one, we go for matrix operations. Okay. Okay. So now we try to solve a system of equations using graphical method. So let's say we have this. Let's say we have some x is equal to 1 and y is equal to 2. I'm developing two equations with those values. So let's say 2x plus 3y is 8. X minus y equal to minus 1. These are the two equations. 2x plus 3y is equal to 8. And x minus y is equal to minus 1. The common solution for that is x is equal to 1 and y equal to 2. And I try to solve that using graphical method. So for that, I have to write these equations in the form of y. Y is equal to something format, like y is equal to mx plus c kind of format. So how to write that? Y is equal to minus 2x by 3 plus 8 by 3. So this is the mx plus c format for the given equation. And for the second equation, y is equal to x plus 1. So I try to plot these two functions. Y is equal to minus 2x by 3 plus 8 by 3 and y is equal to x plus 1. I'm using GeoGebra for that. GeoGebra.org. So here is my first input, 2x by 3 minus 2x by 3 plus 8 by 3. So that is my first equation. Second equation is y is equal to x plus 1. So those two lines cross at a point x is equal to 1 and y is equal to 2. This is the crossing point, and it is a common solution for both the equations. Website is geogebra.org. That is the solution. So this is the graphical solution for system of equations. So you have to write the given equations in the form of y equal to mx plus c and plot all of them on a single graph. So this is the equation, set of equations you have considered. So this is the graphical method of solving system of equations. Suppose you have only one equation. How to solve that graphically? Let's say you have let's say x is equal to 2 and x is equal to 5. So that your function is x minus 2 multiplied by x minus 5 equal to 0. What is that? X square minus 7x plus 10. So this is a kind of equation which you need to solve graphically. Otherwise, take even a simpler equation like a quadratic equation, something like x square minus 4 is equal to 0. That is solve it graphically. How to solve this? So when you have only one variable, separate x square minus 4 is equal to 0. The solutions are plus or minus 2. Okay. So now write f of x is equal to 0 as x is equal to g of x. So the given function is f of x equal to 0. Reset it, rearrange it in a format x is equal to g of x. So you have to rearrange it and get into the format x is equal to g of x. Then you got two equations, y equal to x and y equal to g of x. So to get that into g of x, x equal to g of x format, I'm adding x. So x square minus x plus x minus 4 equal to 0. I'm adding an x and subtracting one x. Okay. So now what is this? X into x minus 1 plus x minus 4 equal to 0. So what do you get? X into x minus 1 is equal to 4 minus x. X is equal to 4 minus x by x minus 1. So that x square minus 4 is written as x is equal to g of x format, in that format. So now my g of x is 4 minus x by x minus 1. How to solve that? I have to plot y is equal to x and y is equal to 4 minus x by x minus 1. So the crossing points are this. -2 and +2. X equal to +2 is one solution and x equal to -2 is another solution. So this same method can be used even in programming language to solve. Like x is equal to g of x kind of function can be solved using a program also. So what I'm doing here, I'm considering f of x is equal to x square minus 4 and my g of x x minus 4 by 1 minus x. Right? 4 minus x by x minus 1. Same. Whatever it is. 4 minus x by x minus 1. So what I'm doing here, I'm starting with some random number and I'm substituting the value of x into g of x. I'm taking some value of x and substituting into g of x. I'll get a new value for x and I'll substitute back into g of x again. And the process continues till I get the solution. How to identify the solution? When you arrive at the solution, the function value becomes 0. So value of f of x is equal to 0 is the location of the solution. Okay. So as long as the value of f of x is greater than 0, I should continue this calculation x equal to g of x. So substitute the value of x into g of x, get a new value of x, substitute again into g of x, get a new value of x, continue it till f of x becomes 0. So I'm starting with some random number as input. It's called a fixed point iteration method. And the compiler you are using is Fortran. The language, programming language is Fortran here. So online Fortran compiler, if you search for it, you'll get it on mycompiler.io website. Online Fortran compiler. right? So we see that. So here A is that set of random numbers, and B is equal to, within round brackets, A less than 0.5. So there is a small correction for the earlier input. The earlier input was this: B of A less than 0.5 is equal to 1. That skips the last number. So to get the full count, we have to write it properly. B is equal to A less than 0.5 within brackets. Less than 0.5. 1. This is greater, 0, less than, greater, greater, 3 zeros, then 3 ones, finally 0. Okay. So now we have to count the number of ones and plot a histogram. Okay, so A is equal to rand 1 to 100. I'm generating one row, 100 columns, 100 random numbers. And what should I do? B is equal to, round brackets, A less than 0.5. So then I go for hist B. I plot a histogram. What do I get? I got nearly 48 heads, sorry, 49 heads and 51 tails. Heads and 51 tails. I mean, that 1 or 2 variation will remain. So these are the 3 simple commands. One, we have generated 100 random numbers, means we have tossed the coin for 100 times. Then B is equal to A less than 0.5, means we are counting the number of heads. Finally, we are plotting a histogram. Histogram of the given data B. So then comes the real question, when you try to toss 3 coins. Yeah, at a time 3 coins, or let's say 4 coins. Let's say you're tossing 4 coins at a time and counting the number of heads. What could be the probability for let's say 0 heads, 1 head, 2 heads, 3 heads, 4 heads? We'll get 5 possibilities. And what is the probability distribution? Do we get each 20% probability? Let's just stick to 3 coins. Okay, whatever. 4 is better. We'll see. So let's say we stick to 4 coin tossing. What is the probability then? Will we get all equal? So we have to look for the possibilities, like 4 heads, 0 possibility is what? All 4 tails. One possibility, 1 tail, 3 heads. Sorry, 1 head, 3 tails. Otherwise, second one head, otherwise third one head, otherwise fourth one head. These are the possibilities for one head. And for two heads, HHTT, TTHH, THTH, THHT, and opposite to that, HTHT, HTTH. So total 6 possibilities. This is 1. And what about 3 heads? HHHT, HHTH, HTHH, THH. You get 4 possibilities for this. And for 4 heads, this is the only possibility. Right, so these are the possibilities. The fundamental rule or first rule of statistical mechanics, first postulate of statistical mechanics is all microscopic states are equally probable. Means how many microscopic states are there? 1 plus 4 plus 6 plus 4 plus 1. Total 16 possibilities are there, and all 16 are equally probable. So now, what is the probability for getting 0 heads? So this is 1 by 16. The probability for this is 1 by 16. And for this, 4 by 16. For this, 6 by 16. 4 by 16. 1 by 16. So these are the probabilities. So for 0 heads, this number is around 6%. This is what? 25%. This one, get some number. This is again 6%. 50, 62, yeah, 37%. So see, the probabilities have changed. So what happened? So now when we toss 2 coins together, let's say, the probabilities of getting 0, 1, 2 are not equal. Our basic prediction says we should get 1/3 count for zeros, 1/3 count for 1, 1/3 count for 2. When we toss 2 coins. but that's not true. That number is now changing, as if like the 2 points are talking to each other, right? So that is the primary observation, and the reason behind this is all microscopic states are equally probable, so which in turn results in a redistribution in the macroscopic outcome. Macroscopic outcomes are not equally probable. And the second postulate of statistical mechanics says, what does it say? The experimental outcome is equal to the experimental outcome matches with the statistical prediction. This is also called thermodynamic average is equal to ensemble average. In pure statistical mechanics statement, it is also called thermodynamic average is equal to ensemble average. So to get the outcome of an experiment, we collect a group of systems and check the outcome. So we take the probability average, and that average will be equal to thermodynamic, whatever experimental average. So here also we have calculated the probabilities using, the outcome percentages using probability theory. Now we do the experiment and see whether we get similar outcome or not. Okay. So now what to do? Coin4. Save the file as coin4.m. So now I have to take 4 coins. For single coin, this is the program. Now I have to take 4 coins. Now my total B is equal to B1 plus B2 plus B3 plus B4. Now I have to plot a histogram with 5 bins. 0, 1, 2, 3, 4. This is A1, A2, A3 and A4. So I got 3 times 0 heads, 27 times 1 head, 37 times 2 heads, 23 times 3 heads, and 10 times 4 heads. So if I run the program again, I'll get another possibility. So I got this higher probability now. Most often the distribution looks like this. 37. Thirty-seven, 27, 20. 8, 6. That's about coin tossing experiment. Next we go for Fourier series. Fourier series means any finite continuous single valued function. What does it say? Any finite continuous single valued function can be written as series of sine and cosine functions. So any finite continuous single valued function can be written as a series of sine and cosine functions. So it is also one kind of power series expansion. Instead of power series, here we expand as a multiples of frequency. So the series of sine and cosine functions will have different frequencies. They are distinguished by their different frequencies. So set of frequency terms can be sine cosine functions. So let's say we try to develop a square wave, let's say. Okay. Fourier series for square wave. So when you add a group of sine waves, ultimately it results in a, so when you add group of sine waves with varying frequency, it will result in a square wave. Okay, so the result is also finite. There is no infinite value, single valued. At any point, you will get only one value for the function. There is no overlapping, there is no crossovers, and it is continuous. There are no gaps. So that is called, in that case, we can apply this Fourier series. So Fourier series for sine wave is given by what? All odd number frequencies of sine function. We have to consider some more all sine functions, all odd sine functions. N value is odd, 1, 3, 5, 7 up to infinity. So we have to take some more all sine functions. Okay. So sin x by n. That is also important. We have to normalize it. So I'm excluding all the numerical constants. I'm considering only sin nx by n. Some more odd numbers. I'm excluding all the numbers, numerical values. I'm considering only the functional form. And I try to plot a function. So I save it as square wave dot m. No spaces. Square wave dot m. And I'm considering x value 0 to 2 pi. So pi is also a built-in function. So I'm taking values from 0 to 2 pi with a step size of 0.1. That is my x value. And I have to calculate some more all odd numbers for n is equal to 1 is to 2 is to 5 or 9. 1 to 9 with a step size of 2. So it takes n values from n values 1, 3, 5, 7, 9. 5 possibilities it will take. And my function f is equal to 0. F is equal to existing f plus sine nx by n. So wherever you are using a group of numbers, you have to consider element-wise operations. Here x is two, so it takes 1, 3, 5, 7, 9, 5 numbers. What I'm doing here is I'm adding sine nx by n to f. Finally, I have to plot x comma f. That is sine wave. When square wave, nearly square wave. So if you want to see what is that happening, I mean, what are the terms you are adding, we can plot them also. External, sorry. So I'm plotting individual sine functions also over the same graph, just to know what are the terms I'm adding. So these are the terms I'm adding, and ultimately I'm getting a square, nearly square wave. Plotting individual terms. You can remove this and check it all if you want. So that percentage symbol is the comment. That term will not be considered. So now if I increase the number of terms, I get more pure and pure sine form. Let's say if I make 90 here, what I get? I get more accurate sine wave. The same way you can plot what other waves are there? Triangular wave, let's say, sawtooth wave. Okay, we go for sawtooth wave. Wolfram.com, Wolfram Math World is a standard reference for this Fourier series. So here you're adding 1/2 minus 1/pi n1 to infinity. We're considering all possibilities. 1/n sine n pi x by L. So 1/2 minus all possibilities of sine nx by n. Yeah. get a better version for square wave. So here I have to add all possibilities, and ultimately I have to subtract the entire function from 1 by 2. So I'm removing this. N equal to 1 to 9. It is sawtooth. Sawtooth wave dot m. Hold all x is equal to 0 to 0.1 to 2 pi. F is equal to 0. N runs from 1 to 9. F is equal to f plus sine nx by n. Sine nx by n. All possibilities. And I have to subtract the entire summation from 1 by 2. So what I have to do? I have to do 0.5 minus f. Plot x comma 0.5 minus f. Got a sawtooth wave. If you want even more clear picturization, take 3 cycles with 6 pi. If I take 6 pi, I'll get 3 cycles of sawtooth waves. That you can take any reference from this series. Let's say you have a triangular wave. Okay. Leave it there. Next one, LCR series phasor diagram. Functional form ఏదో చూడండి. Better functional form. Yeah, this is better. So the functional form is this. Minus 1 power n minus 1 by 2 by n square sine n by x by l. N takes all odd numbers. All odd numbers minus 1 power n minus 1 by 2 by n square. So triangular wave dot m. So I'm taking 3 cycles. I have to consider all odd numbers. So 1 is to 2 is to 9 sine n by x by l multiplied by minus 1 power n minus 1 by 2 by n square. minus 1 power n minus 1 by 2 10 by n square minus 1 power n minus 1 by 2 sin nx by n square. Triangular. తేడా చేసుకుంటారు. Okay, so that's about Fourier series. So now we go for next one is LCR circuit. LCR circuit. So this LCR circuit, inductor, capacitor, and resistor in series, LCR circuit. Right. So here, two things you need to remember. So one is the power factor. So here we are using alternating current to run this fan AC. So it has a positive cycle and a negative cycle. So let's say for the positive cycle, if the fan moves forward, for the negative cycle, it should move backwards. So ultimately, if 50 cycles per second, it should mean we should not see any movement in the fan. One cycle, it should move forward, but next half cycle, it should move backwards. Like that, it should happen. And that is a general prediction when we're dealing with alternating currents. But in reality, it is revolving in only one direction. Why? The actual issue is we are dealing with power. Power is the square of the current. P is equal to V square by R or I square R. So power is the square of the voltage or square of the current. So what happens? Whatever sine wave that is oscillating between positive and negative cycles will now convert it to completely positive quadrant. The power related to that sine wave is completely positive. So that is why that fan moves only in one direction. The work done or power related to that AC current is completely positive. Okay. So now, when you introduce a resistance, sorry, inductor in series. Okay, inductor slows down the current because of induction. So there is a lag, current lags behind the voltage. So in general, voltage and current will remain as it is. I mean, when you multiply voltage and current, two sine waves, you should get completely positive wave. Power is equal to product of voltage and current. Voltage is a sine wave, current is also a sine wave. The product is completely positive. But when you introduce an inductor, what happens? Current lags. Current comes a step backward. So you won't get a completely positive cycle when you multiply voltage and current. So in this case, when you multiply voltage and current, you won't get completely positive number. Some cases you will get a negative component also. Negative power does not exist. So that is called reactance, which is the lag created by the inductor. The same case applies to capacitor. Capacitor leads the current. So current leads the voltage in the case of capacitor. So there is a shift of current in the case of capacitor forward, and in the case of inductor there is a shift back. So in total, these two effects will result in some kind of resistance, which is not actually resistance, it is called reactance. And they are imaginary terms. So we have to show those imaginary terms on a graph. So there is a program already written. LCR. So I took three values of RLC. The resonance frequency is 1 by 2 pi root LC. So this LCR circuit, so apart from all these discussions, what you should remember is inductor allows DC current. When the frequency increases, inductor stops the flow of current, and capacitor allows AC current. Okay, so run the program. See here. This is the voltage passing through the resistor, and red one is the voltage across capacitor. It is moving forward. So the peak shifted forward in the case of capacitor, whereas for inductor, the peak shifted backwards. So I'll share the programs. So during resonance, it is the both inductive reactance and capacitive reactance are equal, and we get only resistive component. And when in the high frequency region, XL is dominant, inductive reactance is dominant. So the curve shifts upwards. And so on the last program in this series is this. Vectors. So here I'm taking a two-dimensional canvas along x-axis minus 2 to 2 and along y-axis minus 2 to 2 mesh grid. And I'm taking various types of functions. One is radially outwards. So the field is expanding radially outwards. Another is radially inward field. So you have minus x and minus y. Another is right circular field. X and y interchange their locations. So first coordinate is minus y, second coordinate is plus x. Left circular means left hand circle. It will be clockwise. Right circle means anti-clockwise. And saddle field, it looks like a spiral spring. Spiral field, gravitational field. So different kinds of fields have been defined. And for each field, divergence has been calculated and plotted. So this is the graph of various fields that were defined. So one is radially outwards. Radially outwards, radially inwards. So the vectors are pointing inwards. Right circular, anti-clockwise. Left circular, clockwise. Saddle means around a point there will be a flow, and spiral looks like a spring. Gravitational field at the center you have maximum and reduces radially. This is exponential field. At a corner you have least P and quadratic field. So these are the various vector fields that we usually come across. Done. So with that, I am closing this session.